Now that I have a new intent of a component, okay, which as we are highlighting now, this is the proposed new design which looks like this. This need not necessarily be a CAD model, because most people, when we would visualize, they are able to sort of they want to have a hasty realization of what their product looks like through a CAD tool. It need not necessarily be a CAD model, it could just be a sketch or a drawing that you came out with as you were having coffee with your friend and you want to investigate it. DFA, DFM allows you to do that even without having necessarily engineered model of your design intent. So, I have this overview of that envelope shape. I am going to take that intent from my design for assembly tool, bring it into design for manufacture. DFMA is a true concurrent engineering methodology, and this tool facilitates that. So, what I am going to do here is take this design intent from design from the software and move it by asking it to open a new file for that envelope, because I want to investigate what it's going to cost me to make that particular new design that I have, and the DFM tool will help us to do it. How? Once I brought it into DFM, what happens is the envelope shape, the number of components I want to make automatically come up from the DFA file. This is one way of doing things. You need not have to necessarily start from DFA to do a DFM analysis. You could do part cost in isolation altogether, but we are just trying to showcase the strength of the tool. Now that you have into DFM, you maximize, you have life volume, which means you need to find out how many number of these parts you intend to manufacture. In most cases, the number of parts manufactured are more than what an organization would require from an assembly standpoint. Why they would do that? Because they want to plan for service, warranty and maintenance inventory also. So, that said, you have the envelope dimensions and you give an average thickness. Bingo, you can start from there and select this process material chart. I do not think there is any tool in the world that can probably help a designer to do this, even if he is not a manufacturing expert, which is to facilitate, given an overall geometry and a volume and a thickness of a part, you select a process, it will tell you what kind of compatible materials are available to do that part in that particular process. Alternatively, you have a preference for a material. Okay, I would like to make it in such and such a material, it will show you these are compatible processes. So, just for the sake of this demonstration, let us look at investigating this part in 3 different materials and processes. We will start with casting. So, we will take a die casting process, we will select aluminum, and as I select these combinations, you will see this process material selection chart shows different colors. So, if I were to see a green color on either side of the process and material chart, which means my selection is apt for the design that I have in mind. If I see yellow, then you see at the bottom left hand of that process material window, it shows you some limitations. Hypothetically, let me create a situation for myself. I will cancel this. I will say, for this overall geometry that we have, what if the average thickness expected by the user was about, say, 12 mm, right. I just input that and I go and select this process material chart. I select the same process and the material. You will see that the warnings that come up at the bottom reflect what are the process mismatches or incapabilities or exaggerations that the user has in mind. That said, DFMA is not pure science. It is a set of guidelines that have been documented over the last 4 decades by our principals through industry best practices, time studies, academic research that is a part of our system. So, though there is a warning that says more than 11.9 mm is unlikely to be practical, you can still, it still allows you to ignore these limitations and explore what would happen if you were to select this process and material combination. And in less than a minute, what you have is on the left hand side what we call as a process chart that is generated for this opportunity that you have, and on the right hand side is details reflecting the process combination that you have chosen, and on the bottom left hand corner is our area of interest, which is the cost implications of the material setup, process tooling and so on and so forth that goes in this in the fabrication of this part. So, you have tooling investment, which is fairly is the mold cost in this case, and the cost of the piece part. Now, if I were to minimize this window for a minute and you look at the design for assembly window from where we actually got this parent part, you will see on the right hand side that the manufacturing cost is captured, which means I could probably be doing designs here and I could be sharing this on a common server where some of my friends or associate or vendors can pick off this design somewhere else in the globe, do a design review of the or do an early manufacturing analysis and throw it back into the same server in a matter of a few minutes. So, that is how we are helping organizations to squeeze their design time by more than 50%, if you recollect my earlier presentation. So, what I am going to do here is we are not going to get into the details of this process of all these process charts, but we have said that DFMA gives you a rapid feedback of your design intent. For example, if I have a process here and let us say in my setup I do not have automatic, but it is manual, what is going to be the implication of this? I select the option, I press on this calculate button under the cost window, and what I get is a comparison of what my current design and what my previous design is. So, this way, even if I am not a manufacturing expert, I have a tool that facilitates us to reflect on the manufacturing opportunities. So, in that interest, let us do a capture of the same intent in two more different processes. So, I am going to have the same design of that envelope and copy and paste it into a new file without changing the reference of the dimensions or the thickness, and we will look at another opportunity maybe to look to explore that part in say sheet metal. And if you look at our process material combination, you will see we have several different sheet metal processes with the subcategories under each of them. So, I will select a turret press and probably low carbon steel, and that combination I am going to get a review of what that component would look like if I were to in terms of cost perspective for getting this manufactured in the sheet metal process. And you will see that I will switch the process from the current casting to sheet metal, and here I have another problem that the dimension that we have taken 12 mm is unlikely to be practical, because we do not have a material library that can actually stamp a 12 mm sheet. What I am trying to say is this tool facilitates as a knowledge base to help the designer get get a rapid feedback of his design intent by saying what is possible and not possible with the criteria that he has selected for manufacturing his part. While it does not stop him from going ahead with his analysis, he knows that these are the problem areas. Instead of facing them at the later stages at the production, at this conceptual stage I am able to get this feedback. At this conceptual stage, when I have not investigated or invested in making a CAD or engineering model, I have a feedback of what my intent is going to be like. So, let me just make one more copy and get this in as a plastic component. So, I will select probably injection mold and maybe a good engineering plastic, say like ABS, as another candidate for exploring this part, exploring the manufacture of this part. And in about 5 minutes what we have done is we had an idea for a part, and we have investigated what is going to be the possible combinations of materials to make this part, and also suitably chosen the processes for it. I like to highlight that what we see here while we are looking at cost angle, just in the interest of this overview, the software gives you detailed analysis of what is the cycle time associated with it, what is the, let us say if you are doing machining, what is kind of detailed parameters related to the volume of material removed, what is the RPM of the spindle speed that is required for cutting that material, and so on and so forth. But at the end of the day, the comparison which leads to time and cost is easy for anybody to comprehend, not only us as engineers who may be using this tool, but everybody else in the organization who can also participate in making a collaborated decision around which is the suitable part or which is the simplified design that one should go after, based on the reflection of our design intent and the output being in terms of time and cost. That is the basis of this overview. A detailed representation of what this tool's capabilities are could be done more intensely. So, at this moment what I have is I had a DFA part, I analyzed it, I came out with a couple of revisions of design. One of the designs I have taken into manufacture, and that is the role I am playing now, and in that we have investigated 3 different processes and materials. But as you see, there are a lot of numbers in the bottom left hand corner. So, we will use the tool, the results generating window to create different reports. One of them is this report for a breakdown of material process and tooling. So, let us expand that as a graph, and I have selected all the 3 opportunities that we have explored. So, in this graph what you get is a one page window which reflects the process material combination selected by the user on the right hand side, the volume implication that he has taken into consideration, and a breakdown in terms of material setup, process rejection and tooling reflected on the bottom left hand corner. So, if you move the cursor on any of those charts, you will get an implication of the cost value and also the percentage contribution. So, I can look at this graph in this fashion. I can break down the graph as a stacked bar graph. So, now the legends are a little slightly different, with tooling, reject, process setup and material reflected on the in different colors. And as you can see, if you move on each of the chunks of the bar graph, it shows you what portion it is, how much percentage in terms of and what kind of cost value. More interestingly, we have another feature which is called the cost versus life volume graph, and again an important tool if you are making decisions, or if you are somewhat like an OEM who wants to negotiate with the vendor as to what is the right mix of this combination. For example, let us say hypothetically, if I move that selection ruler from there to the intersection of the blue and the green line, you will see that if I want to make what 424 parts plus parts, I can actually match casting at the price of plastic, something somebody would want to investigate if he is not interested to have a plastic part for an automotive design. Or if I move that selection ruler to the intersection of the blue and the red line, I am seeing that if I get a number of about 20,000 plus parts, I can make casting appear much more cheaper than sheet metal. So, these kind of decisions are always happening in the industry, but this is happening today based on a gut feel, based on experience and know-how that resides with the organization or with individuals. But with the scientific tool like DFM, what happens is anybody who is curious to investigate his or her design can get a rapid feedback of their design intent, and that is what this tool facilitates. Further, if you are a purely manufacturing person and you have issues in explaining your difficulty of manufacturing the part to the design team, which usually is the case with most organizations, we have an interesting tool called cost reduction guide. What it does is it gives you a breakdown of manufacturing the part and the attributes that are contributing to the cost of that manufacture. For example, in this case it says part complexity, if you move on the graph, is contributing a certain percentage, which is about 25% of the total cost. So, a simple explanation from the manufacturing expert saying, hey, you know what, you have taken 12 mm thickness and that is unlikely for a part like this, or you have that complicated B splines and features. If you were to turn it down to a simple chamfer or a fillet, we will be able to reduce that cost or probably get down that part complexity parameter to a much more manageable portion. So, it is an unbiased way of representing the manufacturing difficulty or capability to the design team, and this works both ways, so that you can make this collaborative decision around your product in much shorter time, in an unbiased fashion, and using some of the best practices that are available without you necessarily having to be a manufacturing or an assembly expert. So, this comes back to a question as how do we get started using DFMA if I want to actually apply to one of my own product designs or parts. So, we would say if you consider your product, look at what is probably the low hanging fruit that you could sort of start to deploy DFM and investigate for results. Like in this case, we are highlighting a hinge assembly. In this case, we have a hinge assembly for use in an enclosure. If you look at the bill of materials and look at the head of that hinge assembly, looks as a good candidate for exploring part count reduction. So, what is this design which is highlighted on the right hand side, which appears to be a 7-part design. Several creative inputs, 2 of them are represented here. One could be a single part cast, or it could probably be a 3-part design from an original 7-part component. And if you were to prototype it, this is what it would look like. Is this a better way to approach it, or if you were to investigate both or more of these design ideas and get a rapid feedback of your design intent in this fashion as shown in this table here, because what this will do is it will give you what is the capture of your original design under these attributes, what is your proposed final design, and of course what are the improvisations you have done. Apart from that, if you are a part of an industry where you want somebody to actually invest into this proposed new idea, what is the profitability or what is the cost of reduced cost at which this product would be built, that becomes a good starting point for exploring an entirely new design. Let me take another example here. This is a product that is supposed to throw out light when you touch a button, right. The main functional parts here are a set of batteries, which is a super system which you have to probably buy from a battery supplier, get them to touch a component which can convert this chemical energy to electrical, and a component that converts electrical energy to light. So, fundamentally if you look at this design, it should have two parts, the one that converts and provides the electrical energy, one that converts the electrical energy to light, but why 17 parts? So, if you look at and investigate it from a fundamental design perspective like that, what happens is what was a potential 17 part component could probably be redesigned to a 6 part tool. Again, this goes through a sort of several cycles of iterations and a common belief among the design team or the manufacturing team that this could be done in a better way, and that was what we would probably like to substantiate or to highlight here, that this tool on its own would not be able to give you intelligent answers, but it is a knowledge tool that can help you to do a rapid product design review, very quick early manufacturing analysis, and give you an update of what your design intent is. So, like I said, we are not here to say let us make cheap products, but the objective is it could be done in a different way, and this tool in a way could help you to investigate that. Just in the continuation, I like to say how DFM has been deployed in the industry. A few examples just for a takeaway at the end of the session. Products that are already into the market, companies are always investigating whether there is a better way of doing it. One of the reasons is basically because new contemporary methods of manufacturing are available. Can we take advantage of that and manufacture our existing product or subsystems in our product in a more effective manner? So, one example here is shown of a flying vehicle like the Apache helicopter, and if you look at the one sub-assembly here which we have taken for today's presentation, this is a tail end of the aircraft called the anti-fail bracket assembly. It used to be a 5 part sheet metal design, and those are the number of operations that go in terms of time and tools. But let us say if I did not have a tool like DFM, and if I were to walk up to my management and propose, let us take a block of titanium and machine it, because we have a 5-axis machining center now, it would look unlikely that they are going to throw in and say or accept my proposal unless I were to probably evaluate this idea through a tool like DFM and chart out a report which I am showing on the right hand side, which is of that review. Again, if you see, the first 4 points highlight from a engineer's perspective that it could probably a single part, no need of tools, it could be probably machined from one block, and also it is lighter in weight compared to the original design. All that is fair enough, but if you look at it from an industry standpoint, am I going to invest into something which is already working and already has certification, already has military certification? They probably would if there is a potential to save on building that particular part, and that is what this tool helps to bridge, to do a review from a design and assembly and manufacture standpoint, while at the same time give you a measure of the probability of doing it much better than it was currently done, thereby helping you to find out and make a decision in an unbiased manner whether the design meets the obligations that the organization would want. Okay. Another example from the aerospace business, aircraft like this, which is a land based system which had about 14,000 parts, had a design review wherein a few more features were expected, like for example in this case the aircraft had to have the ability to fold the wings so that it can be parked in lesser space. So, a product which required 25% more larger size was actually built at 40% lesser parts. So, what was the original 14,000 plus parts assembly turned out to be a 8,000 part design. So, you can see the kind of facilitation DFMA does in helping you to do intense design reviews using this tool. Another example I would like to bring out for part which is used in an unmanned aerial vehicle, the one you see here, is a diaphragm assembly which had about 52 sheet metal parts, and with a few rounds of design reviews, we were able to come out with a product which had just 2 parts made from an entirely different process. So, that is what you see there in terms of the part count reduction and in terms of the number of reduction and fasteners. Sometimes depending on the application, it is not always cost or time. You always have an X factor that drives you to do a design for analysis, like in this case the excellence criteria with the X as we term for excellence. Here was will I be able to reduce the weight, will I be able to make this complex 52 part assembly which had numerous operations and was human driven to assemble be more standardized. That was sort of met. Beyond that, what we were able to do is we were able to reduce the weight of the part. Secondly, increase the resonance frequency, which means for the user these 2 factors are much more exciting than just the cost angle of making this part much more elegant. From an, let us say an example from the automotive space, a product like an HVAC unit which used to take about 202 parts, bill of materials assembled in 342 steps, and each assembly taking about 38 minutes on the shop floor, through a few revisions of DFMA was built with the 47 part assembly assembled in 87 plus steps and less than 8.2 minutes. Now, what does that do for an organization? If you take that 38 minutes and divide by 8, you are getting about 4.2 plus. The same 8 or 10 hour shift, the operators are able to assemble 4 times more number of products without actually causing any other demand in other attributes related to assembling the product. So, that is the, so you are able to improve even throughput or productivity depending on how intensely one can deploy DFMA as a part of the design review cycle. A few more examples here from different realms of industry. Some organizations use it for doing design for service, like organizations like manufacturers who make consumer products, office equipment. Look at this angle of designing a product for serviceability, designing a product for modularity, because when you have a modular design, it is easy that you can sell off that module and can be incorporated in multiple product profiles. Sometimes you look at disruptive innovation and you look at materials, engineering plastics that can probably lead up to helping you make your existing designs much more elegant. For example, taking advantage of an engineering plastic like the one shown here, a 23 part totalizer wheel could be redesigned to a single part. All of the abilities of having the gear, the spring and the numbers all integrated on a singular part. Of course, this kind of activity would require a lot of disruptive thinking, but it is possible and also measurable from a design for manufacturing assembly perspective. Sometimes when you use DFMA, you would like to investigate how the customer is using a product and see if you can probably build integrated products like shown here in this example. What used to be an 18 part assembly for a simple electrical plug, you would investigate how does my customer, would he sit down and repair a wire in the plug, or is it okay to do a fully integrated plug, so that in case it is damaged, all you have to do is throw it away and replace it at a much lesser cost than facilitating for assembly and service. So, different perspectives of a product build, as I said earlier, from excellence criteria is the one that drives out or starts out a design for analysis, and that forms the basis for doing all these simplifications. Example here again is of a 5 part metal blade assembly for a fan redesigned to a single part mold. The challenge is the risk of investing in such a high precision mold, but when it is evident that the benefit of having a lightweight fan blade that could be driven by a less powered motor, helping you to build a highly energy efficient motor design, becomes the basis for doing a review of this nature. I would like to conclude saying what are the areas where design for manufacturer supports. Basically, if you take any product, these 5 steps is what one would visualize in doing the review of the product. One is analyze your current design, identification of what the problem areas is, which fairly depends on the creativity of the team that is investigating this problem. Then come out with again redesigning options for all these problem areas. Again, that is purely human in how what kind of ideas you can come out with, and using this DFA methods to analyze all these potential problem areas that you have investigated and come out with these new proposals, and whichever suits the setup that you have, use that, report it, analyze further for actual adoption. So, these are some 6 benchmarks, 6 pointers that highlight what the DFM is currently being used in the industry and otherwise for deployment. One is in development of entirely new products where there is no reference of existing design, re-engineering existing products, which forms a big chunk of all these new product initiatives that are happening, benchmarking existing in-house as well as competitor products, making accurate cost estimations, because most of the data that lies today with organizations is history based as a legacy. Most of them would like to know what is actual engineering cost of building their designs, and that forms the basis for moving forward. Sometimes the idealistic numbers are so far away from actuals that it is actually surprising, but that starts the process of saying, if that is what idealistic is, where this is where we are lacking, how do we get there, and so that we can benefit, probably benefit the organization or benefit the user of the products that we are building today. So, other things that we probably do is try to investigate and reduce shop floor time by making the assembly even more elegant and more efficient. And the other opportunity is to make decisions of trade off. Today I am making sheet metal, what if I make in plastic? I want it in casting, but I do not like sheet metal. So, what opportunities of volume do I have to provide to my vendor or myself in order to build it at a fairly profitable cost? So, things like this are always happening in the organizations. Today it is done based on gut feel, today it is done based on history, today it is based on who is probably the loudest mouth in the organization. But when you have a tool like DFMA, you can probably make those decisions in an unbiased manner, facilitating everybody to collaborate in this decision making process and probably co-creating or co-owning the revised new designs that come through. That said, I would like to conclude saying thank you for the opportunity. Should you like to reach out to us for getting a trial license of the software or like to evaluate, we will be glad to help, and that is our email address and phone numbers if you like to reach out to us. Thank you so much.